Hello, everyone, and welcome to second semester of General Chemistry, Chem 156. I'm glad you're here. Um, let's go over a few things in terms of the mechanics of the course. And I'm going to start by looking at our Canvas homepage, which hopefully all of you have already visited. But that's going to be one of your good friends this semester, right? You're going to be going back to that page over and over again. Okay. One thing to tell you right away: this CRN number that's here on the course homepage may not be your CRN number. In fact, it probably won't be. All right, because I've combined all the sections into one and it shows the wrong CRN number. So your CRN number is the one on your pipeline account, not on the one here on Canvas. You can find information about me. Here's how to reach me. Here are my office hours. Okay. Here's the link to all the Zoom lectures and all the office hours. Okay. You will always be accessing my Zoom lectures right here. The password is always going to be chemistry. All right. Now, the schedule is a little bit screwed up in terms of what's on pipeline. So the actual schedule is that this class is offered both synchronously and asynchronously. All right. The synchronous part, the lectures on live on Zoom will be Mondays and Wednesdays from 2 to 3:20. And those of you that are here already know that because you're here. But if you can't be here at this time, the lectures will always be posted immediately following right here on the Canvas homepage under class lecture recordings, okay? So if you want to review or if you can't make it sometime, you can always watch it here. Of course, for me, I prefer to have you here in the live lecture with your camera on so I can interact with you and see you and get to know you a little bit. So that'd be my preference. I hope most of you can make it. The pre-lab lectures are going to be posted, are going to be Mondays at 1 p.m. All right. So you may have missed the first one. The first one was today, just before this. And the next one is on a holiday. So the next one is going to be asynchronous. So it'll only be posted here. All right. But generally, the pre-lab lectures will always be on Mondays at 1 p.m. Here's the link to the live lecture, and you'll see them appear here later in the afternoon or early evening. You'll find here the lab schedule. All right. The lab schedule depends on your CRN number. Okay. Notice that two of the CRN numbers are asynchronous. So if you're in one of those two sections, your lab you do basically on your own, and you can go to the professor's office hours to get additional help. All right. The lab is run by these people. All right. So, if you email me with a lab question or if you email me about an extension on the lab, I will refer you to your lab instructor. Okay, so go to your lab instructor for all things lab. Awesome. Very good. I'll come back to this in a minute. The syllabus. The syllabus is right here under syllabus, so you can go to that really quick. You'll find out some information about the course. Again, my contact information, office hours, course requirements. Here you'll see the weighting of the final grade. All right. So labs are 15%, midterm exams are 30%, final exam is 10%. Problem sets, which you'll do in mastering, are 15%. I'll drop one of those at the end of the semester. Pre and post class work is in mastering chemistry. These are assignments that are before class and after class that you will be doing every day we have lecture. Those are 10% of the grade. I'll drop 4 of those at the end of the semester. And then lastly, pre-tests, which are tests that you take online to prepare you for the actual exam, are 20% of the class. All right. The grading scale is here. It's an absolute grading scale, which I stick to throughout the entire semester. And information about accommodations with DSPS are here. And then, of course, the course schedule. All right. The course schedule is built around the chapters 12 through 26 of the book. All right. And you can see what we'll be covering each day and what reading you might want to do to prepare for that. Okay. The reading you can either do before or after the lecture. That's totally up to you, but you definitely want to be understanding this material as we go along. All right. Over here, you can see the exams are scheduled for February 11th, March 18th, and April 29th. Those will be on Thursdays, and we'll start them probably around 1 or 2 in the afternoon, and you can take them anytime between 1 or 2 and midnight. All right. And the final exam is Monday, May 3rd. And again, there'll probably be a larger window than this over which you can take the final, but that's the minimum time. I structure this class and I have assignments because I really am interested in how people learn, and I want the class to be as effective for you as possible in terms of you learning. My goal, my job is to teach you chemistry. Someday when you take an MCAT or you take some exam, I want you to think back and say, wow, Dr. Tro really put in the time and really gave me the kinds of assignments that helped me to learn chemistry. That's my goal, okay? So because I'm so interested in chemical education research, just 3 main ideas. And again, those of you that had me last semester, you already know this, but those of you that are new, you will see in the structure of this course that I'm trying to get you to space out your study, to be consistent and study some chemistry almost every day, right? That's because there's well-documented studies that say that learning that is spread out over time rather than massed together enhances long-term retention, right? And why is that? When you learn something, it goes into your brain, into your neurons, and then your neurons actually take a little bit of time to settle in and put that new information in, right? And so when you come back to it the next day, that information is already kind of hardwired in there, and then you can learn more, right? But if you mass all your learning together, if you try to study for this class by only waiting until right before the exam and trying to learn everything, you'll never succeed, right? So that's why I have daily assignments, right? Daily assignments, problem sets. It's because I want you to space out your learning and take advantage of this. This is the way you can be more efficient with your time, right? You can learn more if you space it out rather than mass it together, even though you're spending the same amount of time. The second effect that's very important is the retrieval effect. I get students all the time that they come to me and say, Professor Tro, I studied for hours and hours and hours and I still got a D on the exam. And I always ask them, okay, so how did you study? Most of the time they say things like, I reread the notes and I read the book. That is called passive studying. Passive studying is not very effective. You got to be active in your studies, right? You have to force yourself to retrieve information, right? To work problems, to answer questions, okay? You got to be active in the process. That's called the retrieval effect. Repeated practice of active retrieval enhances long-term retention. Again, this has been shown over and over again by chemical education studies. And then lastly, pre-testing. Studies have also shown that, hold on for a second, my computer's acting up now. Studies have also shown that if you take a pre-test before taking an actual exam, you'll do better on the exam. So every one of our exams has a pre-test that you will take that'll help you prepare for the actual exam, okay? All right, mastering chemistry. Again, for those of you last semester, you know what's going on here. For those of you that were not in my class last semester, this is something you gotta get on right away. And by right away, I mean today, all right? You gotta get on to mastering chemistry. The way you get on to mastering chemistry is through Canvas and only through Canvas, right? So if there's a home page on Canvas, right? You'll go to the home page and you'll go here, My Lab and Mastering. It'll pop up and you'll click here. And then if you're already in, it'll ask you to sign in with your username and password. If you have one from last semester, it should still work. If you don't have one, you'll be directed to purchase one. I sent instructions about this on an email. I've sent you 2 very important emails so far. They're to your Pipeline account. Make sure you check your Pipeline account regularly. I will be communicating with you primarily that way throughout this course. And every week, I will send you a to-do list for that week so you know what you're doing that week. Because this course has a lot of moving parts. You have the mastery and you have the problem sets, you have the lectures, you have the labs, you have so many things to keep track of. So every week though, you'll get a list and just use it as a checklist and go down the list and do each of those things and you won't miss a thing, okay? All right, in terms of mastering assignments, the first assignment will be a post-lecture tonight, but it's not for credit because some of you may not be able to get on there. The second assignment that's also not for credit is an assignment on mastering itself that'll teach you how to use it. That's due Thursday night at 11:59. But again, that's not for credit. The first for-credit assignment is the pre-lecture assignment for next Wednesday's lecture. And that's going to be due Wednesday at 1:59 p.m. Second assignment is a post-lecture assignment for next Wednesday's lecture. That's going to be due at midnight on Wednesday. And the fourth assignment is the problem set for this week, which will be due on Friday. This will be a familiar pattern throughout the semester. Every time you have a lecture, we have a pre-lecture assignment and a post-lecture assignment. Pre-lecture assignment will be due right before the lecture. Post-lecture assignment will be due that day at midnight. Problem set, do every Friday at midnight. Does that all make sense? I know I'm going through this pretty quickly. Again, you can always go back and watch the video that's posted. Are there any questions?
I have a question.
Yeah.
So regarding the exams, and I'm not sure if this is something you went over, or if it's something I can find on the syllabus, I might have missed it.
Yeah.
How are they going to be administered? Are you going to
On
be
Canvas? They're all
Canvas.
administered on Canvas. Yep.
Okay, so it's not going to be remotely proctored or anything like that?
No, it'll be on Canvas and it'll be very time limited. So that's
Got
the way I try to control dishonesty. I hope you are honest and don't cheat. You will get to use I try to minimize the effects of cheating by giving you a one-page cheat sheet. You can write down whatever you want on that page and use it for the exam. And then the exam will be very time constrained. So you're not going to have a lot of time to look things up on the internet, which you shouldn't be doing. You're only supposed to use the sheets, your cheat sheet, and your own information that you know in your head to take the exam.
Got it.
Thanks, Mark.
Of course.
And sorry, one question.
Yep.
For the practice exams, are they the same way? Like we take them on Canvas and they're similar to the exam?
Those will be in mastering. So those are assignments that will be in mastering chemistry. Yep. And you'll see them come up. Okay.
Thank you.
Hi there. I also have one quick question.
Yeah.
I know it's the first day, but I was just wondering if you were holding office hours today.
Yes, absolutely. Yep.
Okay.
Absolutely.
Thank you.
Yes.
I'm so sorry. I also have another question. So about the lab.
Yeah.
So it says that for like pre-lab lecture, it's like Monday 1 through 2 p.m. I think. But on the thing with like different lab instructors, like some are like asynchronous, so like
correct. So let me talk about that here real quick. The live Zoom lectures for lab, the pre-lectures will be Monday at 1 for all sections. All right. If you can't make that, this course is offered asynchronously as well, right? So you can, if you can't make that, then you can watch the uploaded lecture at any time after that, right? I'll usually post them in the evening, early evening on the Monday. All right. Depending on your CRN number, you're in a different lab section, and those are each have different instructors, right? Those lab instructors, the ones that are synchronous, which are the ones that have a time here, you will join the lab at that time at this link, right? And you will do the lab synchronously with the entire class. Those of you that are asynchronous, like for example, who have Sylvester, that's asynchronous, you'll do the lab on your own, but you can go and ask questions to Professor Sylvester during her office hours.
Oh, okay.
Okay, so that's how it works. Does that make sense?
Yes.
Awesome. Yeah.
Do you think I can switch my lab instruction?
Email me about that offline, Gabby.
Okay, thank you. Thank you.
If you have, let me clear something up. If you have questions, please use the raise hand function on the chat. Sorry, on Zoom, so I can just call on you so that we don't have a lot of people asking questions. Just use the raise hand option. Okay, let's see. Tutor schedule. So we have 3 great tutors. I'm going to ask them to come to class if they can on Wednesday. The tutoring schedule you can find on the Canvas homepage as well. They will have lots of hours available where they're just sitting around on Zoom waiting for you to contact them and get help, okay? So you'll be doing problem sets, you'll be doing pre and post class lectures. You can contact them and get help. They are amazing. And those of you that used them last semester know that. Okay, Armand. Question?
Sorry for interrupting.
No problem.
So I had your class last year for 155, and I just want to double check. Should we buy the lab, like the Hayden McNeil and the Pearson, on the website or from the bookstore?
You can do it either way. Okay.
Okay. Thank you.
But you should always access mastering through Canvas. Okay, very good.
Okay.
Let's see what else. All right, those are all the preliminaries of the details of the class. Again, I will be sending you weekly emails that you can follow, right? And you won't miss a thing as long as you see those emails. I usually send them out on Thursday or Friday for the following week. Okay. Let's see. Katie, you have a question?
Yeah, for the lab.
Sorry, I can't hear you. Katie, you're breaking up.
Can you hear me?
Yeah, I can hear you now.
Okay. For the last.
You keep breaking up. You know what? Stick around and for the after class, and you can ask your question. Hey, Yoon, do you have a question?
Oh yes. So for, I'm so sorry, I totally forgot.
Okay, no problem. Okay, so let's get started. We're going to start talking about liquids, solids, and intermolecular forces. All right, and I wanted to show you a video showing one of the main effects of intermolecular forces. So what are intermolecular forces? Intermolecular forces are the forces that occur intermolecularly, right? So between molecules, right? And intermolecular forces are the reasons that we have liquids and solids, right? So water, for example, is held together in its liquid form by these intermolecular forces. And look what happens when you have water in outer space. Check this out. This is so cool.
Yeah, that's so wild. Trying to push it in. 3, 2, 1. Oh, it made it out the other side. A little too hard.
That is wild.
There, I think it's gonna stay in now.
Yeah, but it's gonna get it from going back down.
Okay. What else can we get inside there?
Isn't that amazing? Right? The water forms this almost perfect sphere in the absence of gravity, right? Now, why does it do that? It does that because of intermolecular forces. So each of the water molecules are attracted to another, kind of like little magnets are attracted to one another. Imagine a bunch of little magnets are all attracted to one another. But of course, there's thermal energy that's shaking everything around all the time. So they're trying to find their optimum configuration. What's their optimum configuration? When they can interact with the most water molecules, right? So they can do that by going into the interior of the liquid rather than on the surface. On the surface, they can't interact with as many water molecules as they can on the interior. So what happens is that there's a minimization of the surface area compared to the volume, right? And that shape that gives you the minimum surface area for a given amount of volume is the sphere, right? So that's why it forms that spherical shape, all right? But that's directly a result of these intermolecular forces, which we're going to be studying, all right? Secondly, all throughout this class, right, I've been sharing with you a theme of chemistry, and that is that structure determines properties, right? What chemists are really interested in is this relationship, right? How does a change in a molecule affect the properties of the substance that molecule composes, right? That's the big theme that unifies all of chemistry. And in this chapter, we're really going to see that theme at play. Look, here are two molecules, right? They have the same exact formula, C2H6O, 2 carbon atoms, six hydrogen atoms, and 2 oxygen atoms. But notice that they're bonded together differently. They have a different structure, right? And they also have very different boiling points, for example. That's one of their properties, right? Ethanol boils almost as high as water does, 78.3 degrees Celsius. Whereas dimethyl ether is a gas at room temperature because its boiling point is below 0 degrees Celsius, right? So why is that, right? That's what we want to try to understand. And in this chapter, you'll really gain appreciation and be able to predict these kinds of things where you can tell, aha, structure, this is kind of what I expect about boiling point. Okay. Solids, liquids, and gases. So remember from last semester, right, we learned about the different states of matter, solid, liquid, and gas. All right. Again, this is kind of a review for most of you. We remember that the solid and the liquid phases are much closer to each other than they are to the gas phase, right? Because the molecules in a solid are held together sort of in a crystalline lattice, like an ice. in liquid water, they're not in a lattice, but they're still almost the same distance apart. They're still fairly close together. But when you boil water, it changes completely and it turns into a vapor, and the molecules are much further apart. Okay. In fact, 1 tablespoon of liquid water would make 8 gallons of gas, of water vapor at 1 atmosphere, right? So that shows you how much space there is between them. You can change between the different states by adding heat. So for example, if you take a solid and you heat it, it'll melt it and become a liquid. If you heat the liquid, you'll turn it into a gas, right? So you can also, though, change between states, especially the liquid and the gas state, by changing the pressure. So if you take a liquid and reduce the pressure, you can turn it into a gas. Or if you take a gas and increase the pressure, you can turn it into a liquid, all right? So we'll be talking about those things as well. You can see that happening in your propane that you use for your barbecue grill, right? When you buy propane, you buy it in a tank that's under pressure, and that pressure, right, forces it to be a liquid, right? But when you open up the valve, that decreases the pressure, and then that makes it a gas, right? So changing in pressure can change between the liquid and the gas states. All right. Throughout this class, I'm going to be using polls because I want you to be actively learning. I want you to think about what we just talked about and answer some questions. So this is going to be our first poll for this semester, and I will launch the poll, and you can answer the question on the poll, and go ahead and do that now. All right, 5 more seconds. Okay, excellent. Thanks for participating. The more you participate, the more you'll learn, right? Because you'll be active in the process instead of passive. All right, so please always participate. The correct answer was A, and look at that, 87% of you got it. What happened? This is a little bit of a review too from last semester, right? When you have a state change, the particles don't change, right? What happens is you separate the particles one from another, right? So the water molecules, you separate them so that there's more space between them. And this is not to scale. This would have to be separated by much greater distances actually than what I'm showing here. But you don't break any bonds. Notice the particles here are different. These are hydrogen and oxygen. This would be an oxygen molecule. This would be a hydrogen molecule. You don't break chemical bonds when you boil water, right? To break chemical bonds, you would have to heat water up to thousands and thousands of degrees. Why is that? Because a chemical bond is much stronger than the intermolecular forces that are holding water molecules together. So if you want to tear a water molecule apart, you have to put in way more energy than it takes to simply boil it, right? Which is just separating the water molecules and putting more space between them, okay? All right, very good. If, as I'm going along, you have a question, I will occasionally ask for questions, but if you have a question, just use the raise hand function, and when I see that, I'll call on you, okay? All right. So the nature of intermolecular forces. So we see the intermolecular forces are responsible. So intermolecular forces. So let me just define them. The attractive forces between molecules. Right, the attractive forces between molecules. And one reason we know these things exist is the existence of liquids and solids, right? Oh, sorry, of molecular liquids and solids. That is, liquids and solids whose individual particles are molecules, right? So things like water, things like propane, right? Things like ice, right? Those are all being held together by these forces between the particles, okay? And those are intermolecular forces, and they're attractive. Now, again, the forces between atoms in a bond, right, are much stronger, right? Why? Because these are interactions between electrons and protons, right, that hold chemical bonds together. And those are big charges at short distances. The forces between molecules are partial charges at longer distances, okay? So they're weaker. That's the main thing. Some manifestations of some types of intermolecular forces, and I did send out a video on this in the email that I sent you. Hopefully, most of you were able to watch that video before coming to class. If you haven't watched that video, this is going to go a little fast for you. So you're going to want to go back and watch that video after class. Okay, there's a link to the video in the email that I sent you for this week. And so please, if you haven't watched that video yet on these intermolecular forces, please do that as soon as you can. So there are essentially three major types of intermolecular forces that occur in compounds, and then one fourth type that occurs in mixtures. So the first intermolecular force is called the dispersion intermolecular force. And that's kind of like the default intermolecular force, present in everything, right? So everything has this intermolecular force in it. Understanding why this force even happens is a little tricky. But basically, we know that an atom, like helium, right, is a collection of a nucleus that has protons in it, and then an electron cloud, right, that is in the area around the nucleus, right? Now, it turns out that this electron cloud can have fluctuations in it, okay? One way to think about that is that the electron, if you took a picture of the electron, right, let's say, which of course you can't do, but if you could, you know, at one moment they might be here, another moment they might be here, and another moment they might be here. When they're in a position like this creates what we call a dipole moment. Well, actually, I should say a temporary dipole moment in this case. All right. This temporary dipole moment means that for an instance, this side of the atom is more negative than that side, right? Because the electrons are over on that side at this particular instant. And when that happens to one atom, it induces a dipole moment in its neighbor, right? Because now these electrons go, there's a nucleus, and they rush over to that side, right? And then same thing happens here and here and here, right? And so now you have these attractions between partial positive and partial negative charges, right? That occur only temporarily, but nonetheless, they're enough that the atoms will be attracted to one another weakly, all right? So these kinds of dipole forces, these kinds of forces are called dispersion forces, and they increase with increasing molar mass, right? So as atoms get bigger, basically what happens is the electron cloud gets more polarizable. It can move around more easily, right? And form a bigger temporary dipole. And so look what happens. These are the noble gases. The only force between these atoms is the dispersion force, okay? And look what happens to the boiling point of the noble gases as you go down the column, right? As the molar mass increases, the boiling point increases, all right? So generally speaking, dispersion forces are present in everything, number one. And secondly, they get bigger as molar mass gets bigger. Does that make sense? Here are some hydrocarbons. We learned a little bit about hydrocarbons last semester. They are compounds that contain only carbon and hydrogen. There are a class of compounds known as organic compounds, right? Or one of the different types of organic compounds. And here we go. As we go from pentane to hexane to heptane to octane to nonane, these molecules get bigger and bigger. These molecules, by the way, are some of the main components in gasoline. All right, so gasoline is composed of these kinds of hydrocarbons. they burn very efficiently and they give off a lot of energy, which when they burn, which is why we use them as fuels. All right. But notice molar mass, boiling point. As the molar mass increases, look what happens to the boiling point. Why? Because the dispersion force, the strength of the dispersion force is increasing, right, as the molar mass increases. Now, molar mass alone does not totally determine the strength of the intermolecular, of the dispersion force, sorry. And look at these two molecules. Here's pentane, here's neopentane. These are isomers of one another. They're made of 5 carbon atoms and 12 hydrogen atoms, right? But they, in this case, they have a different structure. And you already know, structure determines properties, right? So if they have different structures, guess what? They have different properties, even though they have the same molar mass. So this guy boils at 36 degrees Celsius, but this guy only boils at 9.5 degrees Celsius. What that's telling us is that the intermolecular interactions are stronger here than they are here. Why would that be? Well, if we think about intermolecular forces as attractions, right, between these temporary dipoles on neighboring molecules, the temporary dipoles in these two molecules can interact over a larger area, right? Why? Because the molecules are more rod-shaped. These are more spherically shaped, right? So they can only interact over a smaller area, right? So that makes the boiling point of this higher than the boiling point of that, even though they have the same molar mass, and even though the intermolecular force is the dispersion force in both cases, okay? All right, so remember, dispersion force present in everything, increases with increasing molar mass, but of course is also affected by structure. Second kind of intermolecular force is the dipole-dipole force, all right? A dipole, as we learned a little bit last semester, is simply a separation of charge. Right, so you have that, so sometimes we'll write it as partial plus, partial minus. This little symbol here is the delta, and it just means partial, all right? So partial plus, partial minus. Some molecules, as we learned last semester, because of differences in electronegativity between atoms and because of their molecular geometry, are what we call polar. You need to know how to determine if a molecule is polar. So if you forgot that, go back and review that from last semester. But basically, any molecule that's polar is going to have dipole-dipole forces in addition to dispersion forces, all right? So for example, this molecule, because it has a CO here and that O, and that's a very polar bond, this part of the molecule is partially positive, this part's partially negative. The difference between this and this is that in this case, the dipoles are temporary. They only last for a fleeting instant and then they change, which is why this force is weak. But in this case, you have a permanent dipole in an atom, in a molecule, right? And so that interacts with this in a much stronger way, okay? So here are two molecules, formaldehyde, CH2O. Here's their Lewis structure and their space-filling models, right? You know that this bond is very polar and there's nothing opposing it in the structure, so this molecule is very polar, right? Again, to determine if a molecule is polar, you got to go back, draw the Lewis structure, figure out its geometry, right? See if it has polar bonds and see if they cancel or not, right? And in this case, this molecule is polar. Most since the carbon-hydrogen bond is not very polar, and because of the tetrahedral structure here, all hydrocarbons, those things containing carbon and hydrogen, are very non-polar, all right? So this molecule would only have dispersion forces. This molecule would have dispersion forces and dipole-dipole forces. So notice what happens to its boiling point. It boils at negative 19.5 degrees Celsius, much higher temperature than this one. Why? Because that additional intermolecular force between the molecules. Okay. If we were to make a electrostatic potential map of some of these molecules, just showing where the electron density is, we can see how these molecules are polar, right? They have more electron density here than here. So this part is partially negatively charged and this part is partially positively charged. All right, very good. Here is a plot of several molecules that have very similar molar masses, right? So they have very similar magnitudes of the dispersion force. But what we're plotting here is the boiling point as a function of the dipole moment. The dipole moment is just a measure of how much of a charge separation there is. The bigger the dipole moment, the more charge separation and the stronger the force. Yeah? And so you can see that play out here in their boiling points, right? As you go from a very small dipole moment, if essentially propane is nonpolar, to a small, to greater and greater dipole moments, you see the boiling point steadily march up, right? Why? The molecules are attracted to each other more strongly and therefore takes more heat to get them to boil. Does that make sense? All right, so let's see if you can do this. This one's just for practice and the next one will be a poll. Which of these two do you think will boil at the higher temperature? This molecule or this molecule? Just think about it for a minute and then I'll reveal the answer. Which one do you think will have the highest boiling point? This one or this one?
I think B.
It is. It's B, right? It's B because it's more polar. So if you look at the structure, right, you have a CF bond and a CF bond, which is very polar. The CH bonds are very nonpolar, but here the bonds are kind of pointing in opposite directions, so they cancel out a little bit. Here, the bonds are both on this side of the molecule and they don't cancel as well. So this is more polar and therefore will have the higher boiling point. Okay.
So I think I thought different about that one. The way I thought it was polar is because the molar mass of fluorine, yes. Is that right or am I wrong?
No, these molecules are isomers of one another. They both have the same molar mass, right? Because they each have 2 carbons, 4 hydrogens, and 2 fluorines.
Okay, but what about fluorine?
Yeah. The molecules have the same molar mass, both of them. So if you add up the molar mass of both of them, they have the same molar mass, which means the dispersion force is roughly the same in both of them. But this is more polar.
Okay, thank you.
All right. All right, here's one for you to try. I'll open up the poll here, and I want you guys to think about this and answer this question for me. Okay, 5 more seconds. Okay, batting 1,000 here. That's great. Most of you picked the right answer, which was A. Again, you want to look at the structure and determine polarity, right? So the carbon-chlorine bond is very polar. The carbon-hydrogen bond is very nonpolar. In this case, both of the bonds point down, so they don't cancel each other out at all. But in this case, one of the polar bonds goes this way and one goes that way, and they tend to cancel out each other a little bit, right? So this is more polar. A is more polar than B, and therefore A is going to have the higher boiling point. Okay? Very good. All right. These kinds of forces also determine solubility. And there's a very nice, very simple rule that you can follow that says like dissolves like when we're talking about polar and nonpolar substances. All right. So a polar substance will typically dissolve a polar substance, and a nonpolar substance will typically dissolve another polar substance, right? And what that means is that if one substance dissolves another, that means they'll mix. So for example, if you try to mix hexane and water, right? We know hexane is very nonpolar and water is very polar, right? And when you try to mix them, they don't mix, right? So if you wanted to have a substance that would mix with hexane, you'd have to find something else that was nonpolar, Does that make sense?
May I ask why that is?
Sorry, can you say that again?
Why is that?
Oh, yes, great question. So imagine the attractions. So the attractions between polar substances are stronger than the attractions between nonpolar substances. So imagine if you had a collection of marbles that were magnetic. Those are like polar molecules. And then you threw those together and you try to put them in a bin with marbles that were non-magnetic. Those are kind of acting as the nonpolar molecules that have weaker attractions between them. What would happen? All of those magnetic marbles would clump together and separate out from the non-magnetic ones, right? And that's kind of what's happening here. These molecules all clump together because they're attracted to each other strongly, and they exclude those nonpolar molecules. Does that make sense? Taylor, do you have a question?
Yeah, just to kind of add on to that. So basically, the hexene can't penetrate the water. Is that kind of a way to look at it, or?
Yeah. The water molecules all get attracted to each other and kind of exclude the hexane. I mean, the pentane.
Okay, and that's why like water can't dissolve oil.
Exactly right.
Or anything like that.
Exactly
okay.
Right. That's exactly right.
Okay.
Like
I have a question about the nonpolar molecules. How would they dissolve each other if there's no charge trying to pull each other?
So because they have similar forces, so for example, let's say I had pentane and hexane. The forces there would all be dispersion forces and they're all similar. So it would be kind of like mixing, let's say, weakly magnetic marbles with other weakly magnetic marbles, right? So they would tend to mix together.
Okay.
Good question. So polar solvents, if you're trying to dissolve something that's polar, right? You'd want to pick a polar solvent, like water, for example, is very polar. Dichloromethane is very polar. Anything that contains OH groups, like ethyl alcohol, is very polar. Okay. If you want to try to dissolve something that's nonpolar, you would choose a nonpolar solvent, like hexane or carbon tetrachloride or toluene, right? These are hydrocarbons. And again, when you see a hydrocarbon, just carbon, hydrogen, you can just think nonpolar, right? Carbon tetrachloride is nonpolar because even though these bonds are all polar, the tetrahedral geometry makes it so that those dipole moments all cancel each other out. And the molecule itself is nonpolar. Again, if you need to review this, go back to last semester's material to determine how a molecule is polar. All right, hydrogen bonding. Hydrogen bonding is the strongest of the kinds of intermolecular forces that we've discussed. And hydrogen bonding occurs when the molecule contains hydrogen directly, and this is important, directly bonded to fluorine, oxygen, or nitrogen. All right, when you have hydrogen directly bonded to any of those three atoms within the molecule, you have this hydrogen bonding. And hydrogen bonding is kind of like a super dipole force, a particularly strong dipole force. And because hydrogen is so small, the molecules can get very, very close together, and the force is particularly strong because of that. Okay, so you can see it here. This is hydrogen fluoride, and because it has hydrogen directly bonded to fluorine, it has hydrogen bonding, and they get close together, and they can form they have those strong attractions. Here is ethanol, right? CH3CH2OH. These molecules interact. The hydrogen from one can get very close to the oxygen of another one, right? That is what we call the hydrogen bond, okay? You can see it here with the space filling model, the very negative side and the very positive side. And that's, again, sort of a very strong dipole-dipole interaction that's above and beyond the normal dipole-dipole interaction. So for example, here are two molecules that are isomers, again, isomers of one another, same exact molar mass, right? They both have dispersion forces. They both have dipole-dipole forces, right? But because this molecule, look at its structure, contains hydrogen directly bonded to oxygen, it also has hydrogen bonding. Notice this molecule has hydrogen and oxygen, but they're not directly bonded together, right? So you need to look at the structure all the time to determine these sorts of things, right? So because this carbon is bonded to that oxygen and this carbon is bonded to the oxygen, the hydrogens are just bonded to carbons. This does not have hydrogen bonding, all right? Notice the huge difference in the boiling point. 78 degrees for ethanol, minus 22 for dimethyl ether. This is a liquid at room temperature. This is a gas. Similarly, the melting points are affected. This melts at a lower temperature than that because, again, melting is the same thing. You got to overcome those intermolecular forces in order to get something to melt. All right. Hydrogen bonding is ubiquitous in water, right? Water contains very, very strong hydrogen bonds, which is the reason that water is a liquid at room temperature, right? Most things that are as small, most molecules that are as small and light as water are gases at room temperature. But water, because of hydrogen bonding, is a liquid at room temperature. In fact, if we look at the group 6 and group 4A hydrides, right? So here's oxygen with hydrogen, sulfur. This is just marching to the right across the periodic table in group 6. So this is increasing molar mass going this way, and this is boiling point going this way. We see the typical increase in increase in boiling point with increase in molar mass. But look at water. It has this abnormally high boiling point, right? Why is that? Hydrogen bonding. Okay. All right. Let's see. Which of these two? One of these is a liquid at room temperature. The other one is a gas. Just think about it. Don't answer. I want you all to think about it. Which one is a liquid at room temperature? A or B?
It would be A.
It'd be A. Yep. A is the liquid. And that's because it has hydrogen directly bonded to oxygen. Okay. Someone has to mute themselves. Gabby, that might be you. Okay. So it's A. All right. Here's one for you to try. We'll do this on the poll. Go ahead and try this one. Be very careful. Remember, hydrogen directly bonded to fluorine, oxygen, or nitrogen. Okay. Let me give you another hint. Remember that when we write CH3, CH2, etc., when we write the formulas for organic compounds, that means that these 3 hydrogens are bonded to that carbon, right? So that means carbon, hydrogen, 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 carbon, hydrogen, hydrogen, right? Okay, 5 more seconds. Okay, pretty good. A few of you missed it, probably because you didn't realize that the way we draw these structures, what we're saying here is that this structure here is this, This structure here on the left is CHHOCHHCHH. So these are all hydrogens here, right? So does this molecule here have hydrogen bonding? No. Right? It doesn't. Why? Because there's no hydrogen directly bonded to oxygen. On the other hand, this molecule is CHH, 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 NHH, right? And all the rest of these are hydrogens, right? So notice it has hydrogen directly bonded to nitrogen, right? And that gives it hydrogen bonding, all right? So the right answer was B, okay? All right, very good. The last kind of dispersion, the last type of intermolecular force that's important is called the ion dipole force. All of these other forces that I've talked about so far can exist in a single substance. This kind of force is more important for the next chapter that we're going to cover, which is the chapter on solutions, right? Because this kind of force occurs in mixtures of ionic compounds and polar compounds, all right? And it exists between the two different types of compounds. So an ion, like a sodium ion, for example, can interact with the negative side of a water molecule through these ion dipole forces. And these are very, very strong. A negatively charged chloride ion can interact with the positive side of the dipole in a water molecule. And again, this is an ion dipole force. Again, very, very strong. These forces are the reason that sodium chloride dissolves in water. Okay. And we'll talk about these more in the next chapter. All right. So let's try another polling question here that you've seen these different intermolecular forces. Go ahead and try to answer this. One quick thing to remember here, whenever you're trying to decide if a molecule is polar or not, you have to think about its geometry, its molecular geometry. And remember, when we draw a Lewis structure like this, that doesn't always, that's not always drawn in the shape of the geometry, right? In this case, you have four electron groups, 2 lone pairs. Can anybody remember what kind of geometry results from 4 electron groups where 2 of those are bonding and 2 of them are lone pairs?
Is it bent?
Yeah, bent. Yeah.
Absolutely bent, right? So this molecule is shaped like this. And because there are 4 electron groups around here, and sorry, I didn't draw that very well, but because there are 4 electron groups around the carbon, that part is tetrahedral. Okay, but there's this bent geometry that's super important in terms of answering this question. Okay, take about 5 more seconds to try to answer that. All right, so the correct answer was B, and most of you got that. A few of you said dispersion, but the reason that there's also dipole-dipole forces is because of this bent geometry, right? So these are polar bonds here and here, and they don't cancel each other out. Why? Because the molecule is not linear, right? The molecule is bent, so they don't cancel each other out. There is no hydrogen bonding in this molecule. Why? Look at this oxygen. Does it have any hydrogen bonded to it? No, right? So hydrogen bonded requires hydrogen directly bonded to fluorine, oxygen, or nitrogen, and that's not occurring here, okay? Very good. All right. One more question for you. List the following molecules in order of increasing boiling point. Okay, so look at each molecule, look at its structure, and then organize them from lowest boiling point to highest boiling point. Lowest boiling point to highest boiling point. Okay, try to finish in the next 5 seconds or so. Okay, share results here so you can see the correct answer was in fact C. So most of you got that, but this was a little bit of a tricky question. So let's go through here and figure out what's going on. So first of all, let's just figure out what kinds of intermolecular forces are present in each of these molecules. Let's look at this one first. Dimethyl ether. So really that's this molecule here, okay? Because it has an oxygen here in the middle and there's 2 lone pairs on that oxygen, because this is just the structure, not the Lewis structure, okay? This is just the structural formula, sorry, not the Lewis structure. But this molecule is bent, right? Similarly, this molecule is very similar. It's just a little bit bigger, right? But it has the same kind of bent geometry, all right? So both of these molecules have what kind of intermolecular forces?
Dispersion and dipole-dipole.
Exactly right. Everything has dispersion, right? So every molecule has dispersion. But in addition, both of these have dipole-dipole, right? Now, between these two, which would you expect to have a higher boiling point? The smaller one or the bigger one?
Bigger one.
The bigger one, right? Because it has a higher molar mass. So the dispersion forces are even greater, all right? So both of these molecules have dispersion. They both have dipole-dipole. But we would expect this one to boil at a temperature higher than this one because it's bigger and has a bigger molar mass. Now, this molecule, notice what you have here. Hydrogen directly bonded to oxygen. Ding, 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 right? Whenever you see that, you should think hydrogen bonding. And hydrogen bonding is the strongest of all the intermolecular forces. So therefore, this one has the highest boiling point, right? So the order would be dimethyl ether, and then diethyl ether, which is this one, and then N-propanol, which is that one. Okay, very good. All right, let's look at some of the manifestations of intermolecular forces. All right, some of the things that you see as a result of these forces. So first of all, the very existence of solids and liquids, right? Why do molecular solids and liquids exist? Because the molecules have intermolecular forces that hold them together as solids or liquids. So ice, for example, is a molecular solid. Dry ice is a molecular solid. Ice, of course, is H2O. Dry ice is carbon dioxide, okay? But the existence of these in themselves, the reason they exist is because of intermolecular forces. A second manifestation of intermolecular force or really the first of three that are kind of lumped together, is surface tension. So anybody ever fly fish? So you go out to a river, right? You have this fly rod, you tie on this little piece of feathery hook, right? And you try to gently cast it onto the water. And if you're a good fly fisher, if you're good at this, right, you can gently set this thing down so that it will float on the water, right? But if you're not very good like me, you slap it down and it just sinks, right? Because it's actually denser than water, right? So why does it float? It floats because of this thing called surface tension, right? Even though the fly is dense, more dense in the water, it will float on the water, just like a paper clip will float on water if you place it on the water very, very carefully, right? Just take a paper clip, try this yourself if you've never seen it, it's pretty cool. And gently put it on the surface of a bowl of water. And if you're very careful about how you put it on, you might have to use a tweezers. It'll actually float there because of surface tension. All right. And similarly, the reason that we get these spheres in outer space, like we saw in the video, is because of surface tension. So why does that happen? Why is there surface tension? So remember, the molecules are attracted to one another, right? Those attractions lower potential energy, right? So would a molecule have lower potential energy at the surface of a liquid or in the interior of a liquid?
The surface.
So at the surface, they're interacting with fewer molecules. In the interior, they're interacting with more molecules, right? Remember, these attractions lower potential energy, right? So the more attractions there are, the lower the potential energy. So try that again. Which molecule has lower potential energy? The one in the interior or the one on the surface?
Interior.
The interior.
The interior, right? The ones on the interior have a lower potential energy. So all the molecules, remember, anytime that potential energy can be lowered, it typically will. Now, there are some exceptions to that we've talked about a little bit last semester, and we'll talk about again more about this semester. But generally speaking, right? If you raise a pen off the table and drop it, it goes to lower potential energy, right? So these molecules will try to cram in here into the interior to lower their potential energy. That means that that liquids will tend to minimize their surface area, right? And that's what causes the surface tension that causes the sphere. And that's why you can't push this, you have to push this paper clip through that little surface tension, right? Because you would have to increase the surface area in order to get the paper clip to sink, right? And there's a resistance to that. That's called surface tension, okay? Surface tension decreases with increasing temperature, okay? It decreases with increasing temperature. Why? Because as the molecules start moving around faster and faster and faster, the difference between being at the surface and the interior becomes less significant, right? And that's because there's so much thermal energy disrupting it anyway, right? So here's a surface tension of water versus temperature, and look what happens. As you increase the temperature, the surface tension generally drops down and gets lower and lower, okay? Second, and then one more thing about surface tension before we leave that is that it increases with increasing strength of IMF, intermolecular forces, right? So as the intermolecular forces get stronger, surface tension goes up, okay? All right, second manifestation of intermolecular forces is viscosity. Viscosity is the resistance to flow, right? So some liquids like water, for example, would be much more viscous, let's say, than honey. No, sorry, the other way around. Honey would be much more viscous than water, right? That's what viscosity is. It's kind of that resistance to flow that you see in some liquids, all right? Viscosity decreases with increasing temperature. So as temperature goes up, things become less viscous, but it increases with increasing intermolecular forces, and it also increases with increasing molecular entanglement. So look at this group of molecules. Of course, they are getting heavier, but as they get longer, they can tangle up more, kind of like spaghetti noodles would tangle up, right? And that causes a resistance to flow, right? So notice the viscosity here is increasing as these molecules get longer and longer, all right? Really quick, motor oil, the viscosity of a motor oil is a very important property of motor oil. So you want the oil to coat your engine. And so therefore, it has to stay on the sides of the cylinders and things like that. So it has to have some viscosity. But if it has too much viscosity, it can't flow into all parts of the engine, right? That require lubrication, right? So there's this balance of the viscosity of motor oils. And because viscosity depends on temperature, sometimes that could be an issue. So in the old days, we used to have to change the motor oil in a car between winter and summer. In the winter, we'd put in a less viscous motor oil. In the summer, we put in a more viscous one, right? Because the viscosity depends on temperature. Now, what we've created now are what are called multi-grade oils. And this is really a fascinating and interesting application of chemistry. These multi-grade oils are made of molecules that tend to coil up at low temperature and then open up at high temperature. So at low temperature, they coil up, which reduces their molecular entanglement so that they don't get too viscous at low temperatures, right? Because they're all coiled up and they can't tangle up. So at low temperatures, they don't get too viscous. But as the temperature increases, they open up and they don't get too thin because the molecular entanglement increases as the molecules open up, right? So anyway, that's just a little sidebar on engine oils that is pretty interesting. Okay, third manifestation of intermolecular forces is called capillary action. And you've probably all seen this. If you put a small glass tube into a liquid, the liquid will, why is it doing that to me? Stop it. The liquid will actually go up the capillary, right? Now, why is that? Because if you think about that capillary, right? Intermolecular forces don't just occur between the water molecules, right? So these are attracted to each other by intermolecular forces, but they also occur between the water molecules and the sides of the tube, right? The tube is made of silicon dioxide, which is fairly polar. So what happens is that the molecules are attracted to this glass right here, and they crawl up the sides. And as they crawl up the sides, they bring the liquid with them, and that raises up to a certain level, okay? Depending on the diameter of the tube, okay? So this is a way sometimes the blood samples are collected using capillary action. One interesting thing you can observe is the competition between intermolecular forces by looking at the meniscus of a liquid inside of a tube, okay, like this. So this is water, just with some food coloring inside of a tube, and this is mercury. And we're interested in adhesive forces. What are the adhesive forces? The adhesive forces are the forces between the molecules in the tube, right? Compared to the cohesive forces, which are the forces between the particles in the liquid, right? So what do you think? One of these has adhesive forces that are greater than the cohesive forces. Which one is it? Do you think this has the greater adhesive forces compared to cohesive, or this one? Water or mercury?
The mercury.
So good guess, but that's not it. Actually the stronger one is this one, right? Because look what's happening. Here, the water molecules would rather interact with the glass tube than with each other, right? That's what causes this rise up here on the edges, right? But here, the mercury atoms would rather interact with each other than with the glass tube, right? So in this case, the adhesive forces are greater. In this case, the cohesive forces are greater. Okay. All right. Very good. I know I've been going super fast. I haven't really stopped for any questions. So let me take a moment to stop for see if there are any questions. Please use the raise hand option on Zoom so I can call
I'm
in.
trying, but I cannot find it.
Okay. All right. The raise hand option on Zoom is under, I think it's under
Usual metrics. It's under
participants. Yeah, under participants.
What do you want to do with specific?
Okay. Alana.
Just real quick. So the adhesive forces, you said it was between the molecules and the tube, and then the cohesive forces is between the what?
The particles that compose the liquid.
Okay.
So
Okay.
between the molecules in the case of water, between the atoms in the case of mercury.
Okay. Perfect.
Yep. Good. Okay. Gabby, did you still have a question?
No, I just wanted to go to that again. I think you went too fast in this about the adhesive and the cohesive.
Yeah, sorry about that. You're right. So adhesive forces are the forces between the molecules in the tube, and the cohesive forces are the forces between the molecules themselves. Yeah. Other questions?
Sorry, so I think I got it backward then. The water is more adhesive and the mercury is more cohesive.
Correct. That's exactly right. Yep. Any other questions? Abe.
Wait, so why does each one how does each one become either more adhesive or more cohesive?
So it depends on the nature of the interactions, right? The question is, are the attractions between the walls of the container and the molecules stronger or weaker compared to the interactions between the water molecules themselves? In this case, they're stronger, which is why it crawls up the tube. In this case, the interactions between the water, the adhesive forces between the water and the sides of the tube is stronger, which is why you get this shape. In this case, the interactions between the atoms, the particles themselves, are stronger, which is why you get that shape.
Got it.
Okay, awesome. I'm going to introduce vaporization. We just have a couple minutes left, so I'm just going to introduce this topic, and we'll continue with this topic next time. But imagine a beaker of water sitting there on your desk, right, at room temperature. And now remember that the molecules in the interior have lower potential energy than the molecules on the surface, right? Why? They're surrounded by more molecules. There's more molecules holding them together, right? So they have lower potential energy. So the ones on the surface, in a sense, are held a little more loosely, right? So it turns out that because there's thermal energy, some of those molecules on the surface have enough thermal energy to break free, okay? That's called vaporization. And it's the state change from liquid to gas, okay? State change from a liquid to a gas. So first of all, what do you think? Do you think vaporization is endothermic or exothermic?
Endothermic?
Endothermic, absolutely right. It takes energy to do that. Why? Because the molecule, you got to separate the molecule one from another, right? And if they're holding together, the thermal energy, you got to pull them apart, right? So that takes energy. The other reason you know this is endothermic is think about when you're out exercising and you start to sweat, right? When that water evaporates, does that cool you down or warm you up?
Cool you down.
Cool you down, right? That's because the process is endothermic, okay? So the process is endothermic, first of all right? Secondly, the reason it happens, secondly, it increases with increasing temperature. Why is that? Imagine a bunch of water molecules, and here I'm plotting the fraction of the molecules versus their kinetic energy, all right? So remember what temperature is. As temperature increases, we're increasing the kinetic energy of the molecules, right? So if we have a lower temperature, you might have a distribution curve that looks like this, right? At higher temperature, you have a distribution curve that looks like this. Notice the average kinetic energy is higher at a higher temperature, right? So let's say this is the energy that you need to break free from the surface. Look what happens. At the lower temperature, only this fraction of molecules has enough energy to break free. But as you raise the temperature and you shift the molecules towards higher kinetic energy, now more molecules have enough energy to break free, right? So that's why vaporization increases with increasing temperature. Now, what if you were to take your beaker of water and spill it on the floor? And I just want you to think about this. If you had a beaker of water on your desk and you watch it evaporate, how long would that take to completely evaporate? Probably several days, if not weeks, right? But now imagine taking that same beaker of water and spilling it on the floor. Come back the next day, it's probably dry. Why is it that when you spill it on the floor, it evaporates so much more quickly than when it's in the beaker?
Greater surface area.
Surface area.
Exactly right. So this increases with increasing surface area, right? And why is that? Well, we already know, sorry, I can't write here towards the end of this lecture. We know that the water molecules at the surface are held less tightly than the ones at the interior, right? So because of that, they evaporate more easily. Okay, I have a question from Ian.
Yeah, so is there a difference between vaporization and evaporation, or is it the same thing?
Those are the same thing.
Okay, awesome, thank you.
Yeah, great question. Okay, folks, we are out of time. So I'm going to officially end class, which means I'm going to stop the recording. We'll meet again on Wednesday at the same time, 2 p.m. Thank you so much for your attention. Thank you so much for your participation. Even though I'm ending class now, I will, of course, stay on because I have office hours for the next hour and 10 minutes. So feel free to stay on and ask me any questions you would like, or just hang out and chat. I'm happy to hang in there with you and chat. Okay, so I'm going to stop the recording. Thanks, everyone. See you on Wednesday. Bye.